competitive students drone team in the Netherlands.
Throughout my life, I've always been very interested in anything that flies. Fascinated by the freedom of flying.
The industry is so young that any changes you make to a normal drone will have a bigger impact in the future.
Thereby achieving our mission to innovate and accelerate the drone industry. We do this by developing drones for humanitarian aid. Drone Team Twente.
Hello everyone and welcome to this Drone Team Twente design review. I am Sietse, I'm the team manager of this year. And when you start your student team year, the first 2 weeks are pure chaos. The question on your mind constantly will be, what? What am I going to do today? What am I going to do in 2 weeks? And what am I going to do the next year? After that subsides, the question of why comes to your mind, especially as a manager. And to answer that question, I would like to tell a story that happened in Rwanda in 2019. So, one evening, an emergency call came in. There's a baby in critical condition and it needs blood. The problem is that the infrastructure is bad and the target location is 105 kilometers away. An ambulance would take 3 days to arrive there. 5 minutes later, a drone is cleared for takeoff at Rwanda airport. And the drone starts its mission and travels in 40 minutes to its target, drops off the blood, and returns home. The mission is successful and the baby is saved. Now, this story is short, but it is true, and it illustrates why drones can really make the difference between life or death in some situations. And this is an example from emergency response, but the drone industry is a very novel, growing industry that is also growing in terms in uses of film, agriculture, building, and even firefighting. Drones don't care about bad infrastructure. They can go wherever they want. They don't care about trees or buildings or bad roads. And because we want to make this industry grow even more, we want to accelerate it. And that is half of our goal. We want to accelerate the drone industry. And we want to do this by innovating. So to innovate and accelerate the drone industry, that is our motto. And this covers the what and the why of what we're doing this year. But there's another question. How? How are we going to innovate and accelerate the drone industry? And to answer that question, I would like to invite my technical manager, Philippe, on stage to explain that.
Thank you very much, Sietse. Hello everyone, my name is Philippe, and I'm the technical manager of Drone Team Twente. Now, to properly answer this question, I would like to take all of you back to the beginning of the second year, when a group of 14 ambitious drone building students came together to sit around a table, around the drawing table, to basically discuss what our goals for this year would be and what we actually wanted to build. These sessions would always go over time, and in these sessions we would always discuss, do we want 1 wing, 3 motors, 4 stabilizing flaps? But one thing that was obvious after a couple of minutes was that we wanted to continue our participation in the UAS challenge. Now, you must be wondering, what is the UAS challenge? As a drone team, this is our 4th year participating in the challenge, and over the past 3 years, we have won 2 awards, which are the most innovation award in 2020, and the most promising award in 2021. Now the goal of UAS Challenge is to build a drone that you can place somewhere. It flies to point A and back. The goal is to build a drone which can deliver a package of up to 3 kilograms. The goal is to identify a 2x2 meter white matrix on the floor and send that exact location back to home base. Now besides having chosen our challenge, we had to get started with the drone. What did we want to do? Because in drones, there's so much you can innovate. There's so many different options. And what we first already chose was that we wanted our drone to be VTOL. VTOL meaning vertical takeoff and landing. This meaning that we can take the drone and put it in where we want, where there's a clear airspace, and let it take off from there. Now this is a crucial point if you keep the mission of humanitarian aid in mind. Because we want to be able to hover above a point, drop a package on a precise location. During disaster areas, during disaster times, this is amazing. But also, we don't want to have to fly over a point to just miss the point with the package, and in the end, missing the point of humanitarian aid. Another goal that we had was to make our drone durable and modular. Modular because we want to be able to take our drone everywhere and put it in and set it up really quickly. But also, for the case that we crash, we wanted our drone to be durable so that we could reuse as much as we can of the drone for future purposes. Furthermore, this is an important aspect when going through the prototyping phase. You want to iterate as much as possible, and what we've been told in the beginning of the year is that you will crash. I know it's not a great sight to look upon, but it's great to start somewhere. This year we decided to focus on an innovative design. We wanted to build a drone that Drone Team Twente has never built before. We wanted to build a drone that the drone industry has never seen before. We wanted to shock the drone industry with this design. But all these goals are not met easily. It takes a lot of hard work. And in that hard work, we do hours of aerodynamic simulation, days of electronics testing, and weeks of structural building. Now I'm very proud to stand here in front of you all today. And so my team is also very proud to be able to present this drone to you here today. This drone is fast, electric, innovative, and groundbreaking. I am proud to present to you today Drone Team Twente's new drone, Thunderbird. Such a beautiful drone. Unique and innovative. Now you might wonder, how can I myself build a drone just like that? Well, I brought my technical team today to take a deep dive into the drone itself and peeling the drone layer by layer. First, we'll start off by the frame and the build of the design by analyzing the aerodynamics. After that, we'll dive into the material by talking about our structure. And at the end, we'll literally put you guys inside of the drone to talk about the electronics and how the drone itself flies. I would first like to invite Max into the stage to tell you more about aerodynamics.
My name is Max Thank you, Philippe, for your nice introduction. And I'm here to talk to you a little bit about how we get our drone to fly. So, Thunderbird. Most of you probably haven't seen a design like this before. If you were to look in the sky and you see this drone fly high in the sky, you might think to yourself, is it a bird? Is it a plane? Is it a quadcopter? Well, it's a lot like a bird, plane, and quadcopter, I'd say. Because, like a plane, our drone, as Philippe mentioned, transitions into a horizontal flight mode, which uses its wings to sustain itself during flight, preserving some vital battery power in the process. However, like a quadcopter, it takes off using its downwards facing propellers and can hover in the sky and requires little infrastructure for that reason. And much like a bird, we do expect our drones to fly. So that's an important aspect as well. Anyway, so our design, the Rembodio wing. You might think, what is this thing? I've never seen a wing like this. It's pretty unique, right? Well, formerly this could be called the parental wing or the boxed wing design. And it offers a lot of advantages aerodynamically, including stability, etc. But we'll get more into that later. And it just looks pretty cool. So that's another good reason to pick this design. Ludwig Parental. We have him to thank for this design. He's a scientist and mathematician. And back in the 1920s, he did research on aerospace and basically created the foundation of the mathematics behind aerodynamics. So he's a pretty important figure, and back in the 1920s, he visualized this concept as a concept that minimizes lift-induced drag. And it has other benefits like not having wingtips and being more stable in different axes, and it doesn't generate vortexes at the end of the wings. So it's a pretty cool design, pretty unique. However, why don't most planes look like this? Why isn't this the standard design if there's so many benefits? Well, despite its advantages, it's very hard to manufacture a plane like this. It has complex structures supporting the wings together, and the horizontal stabilizer is connected with the main wing, which on a big scale would be practically impossible to build, in addition to it being very difficult to compute mathematical calculations on it. Despite this, we thought with a smaller scale, because now unlike the 1920s, drones are a thing now, and we can control smaller objects and make things fly with electronics rather than requiring big infrastructure. So we gave Parental's vision another chance to see the light of day. And additionally, using additive manufacturing methods like 3D printing, it's actually quite doable to manufacture these complex hinges and connection points. So, we started, as Philippe said, with the concept. Back in October, we came up with many different designs and weighed the pros and cons of all of them. Our biggest two contenders were Flying Wing and the Rembodio design. And because of its benefits with the stability and the reduced drag, we chose this design in the end and decided to model it. So what we do with a model like this, well, we can perform calculations on it using a simulation software. And that's what aerodynamics does. We optimize our design using analysis and iterations, using a software called StarCCM that performs something called CFD calculations. CFD basically simulates the airflow as a vector, every particle as it passes around the wings, and can simulate how much force the wings push up and what the stability is and how much the back wings push up compared to the front wings, etc. And it's all done by simulating the airflow. And that's pretty much impossible to do by hand, right? So another important aspect of aerodynamics is not just calculating the air as it flows around the wing, but also how it balances and if it's stable in the air. A drone or a plane that has too much weight at the front of the plane in respect to its center of gravity has a tendency to maybe fall down, and the opposite is true as well. So it's important to balance the weight as it's important to balance the lift, because if the rear lifts more than the front, it also tilts forward. And that's what we have aerodynamics for. Next, so aerodynamics also make sure that the drone maneuvers in the air. And how does a drone maneuver in the air? Well, much like a sailboat in the sea, a drone uses the same type of technologies in the air. It uses something called control surfaces, which you can see here, to manipulate the airflow as it flows over the wing. And if we want the drone, for example, to turn left, we use something called an aileron. An aileron is typically located at the tip, at the end of the main wings. However, our design has it on the back wings, but it's still kind of located at the same location. If one aileron pushes one wing up while the other one pushes it down, then the drone has a tendency to tilt one way, and the opposite is true. Now, how does a drone change in pitch and go up and down? Well, that's what we have elevators for. Elevators are located at the rear of the wing, and all planes have this, including like commercial planes. If you look at a normal plane, it has a main wing, and then it has a horizontal stabilizer, another wing at the back. And on those wings, you see something called elevators. Elevators manipulate the airflow in the same way, and because of the location all the way at the end, it has more of a moment and has more control in like swaying the entire plane up and down. Finally, we have something called a rudder. A rudder is positioned also at the end, but it's instead of horizontal, it's vertical. And this allows for a plane to rotate without changing pitch. It rotates left and right horizontally, and that's why it's positioned vertically. This is good if you're close to the ground and you can't afford losing altitude, or you're gonna hit the ground if you're rotating, right? So finally, this is how we fly the plane in horizontal mode. However, as was mentioned, our plane also combines the properties of a quadcopter. Just like a helicopter, a quadcopter, heli means one, quad means four. It has four propellers that push the plane with an equal force down. If the four propellers are pushed with an equal force, the drone would just fly up and down proportional to how much energy you put in the engines, right? But if you change the power balance and you give the rear propellers more thrust than the front ones, then the drone has a tendency to tilt forward and fly forwards. That's how a quadcopter flies. And the same is true for left and right. And then for turning horizontally, that's a bit of a more complicated maneuver. And performing aerodynamic calculations is quite a drag, but that's not all. There's more to a drone, because no matter how well the aerodynamics function, the drone has to be able to sustain itself. It has to stay sound in the air, and that's what we have structural for, and that's what we have Sherman to thank for. He's here to present the structural design and how the drone stays intact. Thank you, Sherman.
Thank you, Maxine. I'm Shervin, the structural engineer of Drone Team. Now we're going to dive deeper to understand how we bring this physical airplane from the software to this. Well, the first challenges we face is the weight limitation we have. By the competition, we are limited to 10 kilogram weight when there's a payload inside this drone. We tackle this problem by two parts. First, we use a carbon internal skeleton, which you can see behind me, that is enforcing entire this plane. It carried all of our load. The second part of the solution is we do a lot of material testing, and usually we end up with exotic plastics such as lightweight PLA. Lightweight PLA is a family of PLA that use widely with other 3D printings. However, lightweight PLA gives us the capability this drone becomes 6 times lighter if we build it out of that instead of PLA. The second problem is we want to be able to transport this drone. If you want to transport it like this, it's pretty hard. So we have a transporting box. But however, we have to design this modular enough to transport it. Usually when we try to create this drone more modular, we lose stiffness. We attack this challenge by dividing this drone into 6 pieces, where our 4 wings can be disassembled with the side wings, and we have 6 parts. All the 6 parts can be put in the box and be transported and reassembled and have the stiffness of the drone intact. However, this drone will be impossible to fly without a control system. And this is why I'm going to invite our control system specialist, Renz, to tell you more about it. Thank you.
Indeed, thanks for pointing it out, Shervin. While a good aerodynamic model and effective manufacturing methods for lightweight structures are a really important part of drone development, the drone will not be able to fly without the help of my sub-team. I'm Renz, and I'm part of the electronics and control system. We ensure that all the electronic parts cooperate to keep the drone in the air. Next to that, we are in charge of planning the autonomous missions. Here we need to configure all the different functions the drone should perform during its operation. Since the flight is fully autonomous, we need to know the drone inside out in order to ensure a correct, reliable, and most importantly, a safe flight. Looking at the drone, arguably the box wing design is the most eye-catching part of this drone. However, you might have noticed the 4 different motors placed around the vehicle. These 4 motors are the VTOL system, which has been mentioned before, but just to reiterate, stands for vertical takeoff and landing. If you came to this event without having any expectations, maybe you thought that you would see a somewhat smaller vehicle with only these 4 motors, as this is what people often think about what a drone is. But it doesn't need to be. We still chose this design since we are able to land and take off without needing an airstrip, which is especially crucial for the humanitarian drones, since we intend to use them in regions that generally lack this kind of infrastructure. The control system behind the VTOL system is quite ingenious. If you had to control all the motors by yourself, so tweak all the individual angular speeds, you would for sure crash. There's no way to do that. Luckily, there exist flight controllers. These small computers can do all the hard computational work for you, such that you only have to give general inputs like go forward or rotate. Next to that, they are able to self-stabilize the drone, or in our case, even be able to carry out complete waypoint missions without a pilot. They really are the brain of the drone. Another part of electronics, which is much less focused on the motion of the drone, is image recognition. By attaching a small camera to the setup, we can give the drone vision and increase its capabilities. We use this image recognition for 2 different reasons. Our main reason is that we want to use the drone to locate objects. So if an object is spotted, it can send pictures like these to people, which they can anticipate upon. However, having only such a picture is not enough, since people still don't know where exactly this object has been found. It's just a picture. If you don't know the region, you have no clue where it is. For this reason, we wrote code that uses information about the drone from the flight controller, such as its position, so we can better estimate where this picture was taken and where the exact object was found. However, in this setup, we still rely on people to take action. We wanted to go even a step further and let the drone make decisions itself based on what it sees. For example, if we're only looking for one object, we might want the drone to just go back to its home position, where it took off, since we knew where it was located. Or maybe hover in the air to get some better footage of this object. In order to achieve this, all the image recognition needs to be done on the drone itself. To make this work, we needed to add a small computer inside of the drone. This computer then needs to be connected to all the different electronic parts, such that it can send commands to the flight controller, which can then instruct the drone what to do. So effectively, based on what it sees, sends commands and tell the drone what it does. This was not easy to accomplish, especially as drone developers. We still want to be able to see what the drone is doing and get updates from the drone, and make decisions ourselves based on what it does. In this way, we need to have a laptop on the ground, which is called a ground base, which then connects to this flight controller. This poses a problem, since now there are two different devices telling the drone what to do. We, at the ground, with our laptop, are sending commands, but also this computer inside of the drone. Within the electronic subteam, we have to ensure that the wishes of both of the devices are respected by the flight controller, and thus it doesn't get confused by these double signals. Next to that, we also want to have some information about the image recognition results, so have a direct link between the laptop or the computer inside the drone and our laptop. This is quite difficult, since we intend to use this drone in regions that generally lack a Wi-Fi signal, or maybe don't even have access to a 4G network. So we need to have some clever tricks to get the data from this PC back to our laptop. In order to solve this issue, we needed to dive deep into the firmware of this flight controller and figure out how it sends its data to the laptop via a telemetry link, which is a radio signal. Once we figured out that that works, we could send our own custom data over the same link and send it to the laptop. In this way, we can let the drone fully do its own thing, but if we want to take over, we still have that possibility. Well, there was quite a lot of technical information to take in, for me, but also for Maxim and Shervin. But hopefully you've been able to see the technical progress the team has made, and how we as drone team are pushing drone innovation. However, this is not only something done by the team itself, but this can better be explained by our technical manager Philippe, which I invite to the stage.
Thank you very much, Lens, Shervin, and Maxim for explaining all the technical details. Before they started, I proposed the question, will you guys be able to build this drone yourself? And I hope the answer to that is yes. I hope that you guys have gained enough knowledge to go home and build this drone. But as I said before, it's okay if you don't. We built this in half a year. I don't expect you to do it in one night. But I would like to give a special thanks to our fundraisers and our sponsors. Especially to our sponsors, the people who have funded us in either funding or components, but especially for the collaborations. This year we decided to take collaborations to a different level. We started working together with Sekisirikase, a foam-based company, to see whether we can use their material that is recycled from PET bottles, and use that for drones itself. to replace the structure and eventually making the drone industry more sustainable. And in that way, also kind of innovating and accelerating the drone industry. Now, I really hope that you guys understand our mission. The mission, of course, has two parts. Innovating, and innovating happens within our office, happens within our workshop, and it happens right here. But then the accelerating is what is the most interesting part, is what we tried to bring to companies. And this year we decided to take another approach to that. We decided to sit together with startups, new companies that just got into the drone industry, and see how can we help them, how can we give our information, the stuff that we've learned, onto them, and how can they help us. These are key steps to accelerate the drone industry.
Stories like the one in the beginning about Rwanda motivate us to work even harder and innovate even more and build even more drones. And we hope that the flap of our little wings will ripple through the drone industry and will create a storm that will eventually save human lives. For now, we're focusing on our main challenge, the UAS challenge, which we'll be going to in the beginning of July. So if you're interested, please follow us on our social media. And to end this presentation, I want to thank Concordia for letting us host this event. Studio Mad for the beginning, or the video you saw in the middle of the presentation. And thank my team for making this year possible. And thank you, the audience, for listening. Thank you.